Hi everyone. Today I am going to walk you through an exciting project I built called Multitask Learning with Gradient Surgery using TensorFlow and Streamlit. Okay, if you ever wondered how to train a machine learning model to handle multiple related tasks at the same time, especially when those tasks have conflicting signals, then this project is exactly what you need to see. Okay, let's dive in. Okay, coming to the problem statement. Imagine you are building an AI system that needs to accomplish two related tasks simultaneously. For example, predicting if a customer will buy a product and predicting if they'll write a review. Okay, these are the two tasks. Okay, these tasks are related, but they can send conflicting signals to your neural network. When you try to optimize for both losses at the same time, the gradient can pull the model in opposite directions. This is called gradient conflict. Traditional approaches just add up the losses and hope for the best. But what if we could be smarter about it? Okay, that's where PC grad project conflict gradients comes in. It's an algorithm that computes the gradient for each task separately and detects when gradients are in conflict and projects out the conflicting paths and updates the model intelligence. Okay, next coming to the architecture, let me show you what I built. The architecture has three main components. The first one is a shared backbone. This is a dense neural network with an input layer, a dense layer with 64 units, batch normalization for stability, another dense layer with 32 units, and dropout for regularization. Okay, this backbone learns features that are useful for both tasks. And the second one is we have two specific heads, task specific heads. Okay, each one gets the shared representation and adds a dense layer with 16 units, outputs a single probability for binary classification. Okay, task A and B each have their own head, so they can specialize while sharing the backbone. The total model just 4258 parameters. Okay, and coming to the third one, we have the PC grad algorithm. It runs during training and watches the gradients from each task, calculates cosine similarity between them. If the conflict similarity is less than 0, it projects them apart. Then the optimizer applies the adjustment gradients. Okay, let's talk about the data. The dataset is synthetic, which means the project is completely self-contained. No external data needed. We generate 2400 training samples, 600 validation samples, 600 test cases. Each sample has 12 features. Here's the key part. The tasks are intentionally conflicting. Task A has a positive correlation with the main feature. Task B has a negative correlation with the same feature. This creates a realistic gradient conflict that PC grad can demonstrate on. We use deterministic seeding so you get reproducible results every time. Coming to the training approach, I implemented two training approaches to compare baseline training and PC grad training. Coming to the baseline training, computes task A loss and task B loss and adds them together and back propagates through the entire model. No conflict resolution serves as a control to show why PC grad matters. Okay. Coming to the PC grad training, uses a custom TensorFlow training loop with gradient type. Computes separate guidelines for task A and the backbone. Computes separate gradients for task B on the backbone and calculates cosine similarity for that. And if the conflict is less than 0, it applies gradient projection. Logs with similarity at every step. We get a beautiful visualization of conflict over time. The PC grad loop demonstrates that we have handled conflicts intelligently, both tasks improve. Okay, coming to the dashboard, there are three main sections in the dashboard. First thing is gradient conflict monitor. This is a line chart showing cosine similarity between gradients over training system steps. Watch for the red scatter points. Those are the moments where conflict was detected. You can literally see PC grad doing its job in real time. Second one is performance dashboard. Four subplot comparing. Task A accuracy, task A F1 score, task B accuracy, and task B F1 score. Notice how PC grad consistently outperforms the native baseline, especially on the conflicting tasks. Representing inspector. A beautiful 2D visualization of the shared representations that the model learned. We use UMAP, a dimensionality reduction technique, to see how the model separates the two classes into 2D space. You can toggle them task A and task B labels and adjust the sample size. All of this is built with Streamlit, so it's interactive and real time. Okay, coming to the Docker and reproducibility, one thing I really care about this reproducibility. So containerized everything with Docker. To run this project, you literally just need two commands: Docker compose up hyphen hyphen build. This that it Docker pulls a Python 3.11 image, installs all dependencies, TensorFlow, Streamlit, Pandas, everything, and starts the dashboard on port 8501. Now it's work on my machine. Problems. No dependency conflict, it works everywhere. The Docker Compose file also sets up environment variables, volume, bounds, and proper port binding. Everything is configured for production. Okay. When I ran the training, here is what happened. The baseline models learns both tasks, but because gradients are conflicting, it is a compromise. Some loss is wasted fighting itself. The PC grade model detects this conflict. We see it in the gradient conflict CSV and projects it away. The result: better accuracy on task A, better F1 score on task B, more efficient learning, smoother training curves. All metrics are automatically exported to CSV files, and the training weights are saved so you can load them later and make predictions. Okay, this entire project is an open source on GitHub. The link is in description. You can clone it, run it, modify it, learn from it. If you found this interesting, please check out the repository. Start it if you think it's cool. Poke it or try your own multitask problems. Let me know what you're build with. Thank you for watching. I hope you learned something new about multitask learning and gradient surgery. Okay, see you in the next one.